Hello everyone. In this video tutorial, we are going to discuss the concrete damage plasticity material model in ABAQUS or CDB model. We are going to discuss the actual definition of the material model quickly, what are the main parameters and the property definitions that you need to define this material model in ABAQUS. And then we are going to show quickly the actual implementation step by step and how to deduce different material parameters and how to input those in ABAQUS in order to simulate the elastic, the plastic response, in order to simulate damage, and in order to simulate as well failure, and if you want to visualize element deletion, which many of you are interested in. So first of all, the CDB material model has a number of material definition. The basic one is the elastic property, similar to most of the material models. So you need to define the elastic property or the elastic material response pretty much. And then there is the plastic property, and this is where you define the stress strain behavior in the plastic range or the inelastic range. And basically define other parameters to characterize the flow rule and the evolution of the yield surface of the material model. And finally, we have the damage property, and this is an optional. This is actually a sub-option of the CDB model. And this one refers here to the deterioration of the unloading, reloading stiffness of the material, all right? Under cyclic loading. So actually, if you are dealing with a monotonic loading scenario, you can ignore this property definition. So to define the material, well, clearly you need to have beforehand the stress strain data of your concrete material under compression and tension as shown here. So this is the compression stress strain behavior, just an idealized curve shown here, and you need to have as well the tension part, the concrete behavior under tension as well. And these are some of the parameters that you need to be familiar with, like just for notation, similar to what ABAQUS uses. So this is the crushing strength, and this is pretty much the yielding, the compressive strength of concrete. Well, concrete is not yielding, of course, but I mean this is the onset of plastic deformation. So this is the end or the theoretical end of the elastic branch. And in the tension side, you have here the ultimate or tensile capacity beyond which cracking will happen, and then the material will start cracking and tensile damage will happen. So basically, it's generally recommended when you define this data actually that you get this stress strain data from a cylinder test. Well, basically under compression, I mean. You get this from a cylinder test rather than a cube test. Because a cylinder test is a more realistic representation of the actual confinement of the concrete. Well, this depends on the problem in hand, but in general, it's preferred to use the actual cylinder test data. If you have data from a cube test, you can actually do an approximation where you reduce the stress values by a factor of about 0.8. All right, so what will happen if you don't have this kind of data? If you only have, let's say, the crushing strength, like you know the grade of the concrete, like you know the crushing strength, and perhaps you know the elastic modulus or something like that, how can you define this data? There is a lot of expressions available in literature, so you can use those. If the complete stress strain data is not available, you can actually use these expressions to generate the stress strain curve. One example is Eurocode 2. Eurocode 2 provides an expression for concrete in compression, and this is how the curve will look like using this expression. So this is the expression over here from Eurocode 2. And basically what you need in order to define the stress and strain relation, you need to know a couple of parameters. You need to know the modulus of elasticity of the concrete. You need to know the strain corresponding to the compressive the ultimate compressive strength. That's it. If you don't have those, again in Eurocode 2, if you go to table 3.1, you can actually, knowing the grade of your concrete, you can go into this table and you can deduce, or you can obtain these values. And then once you have these values, you just plug them in Excel or something, and then you can generate this stress strain curve here, and then you can use it, of course, later on in ABAQUS. With respect to the tension part, if we are looking into the concrete behavior under tension, there are a number of expressions available in literature, again, to generate the softening behavior of the concrete in tension. So softening here, I mean this branch after cracking happens. So this branch that you see over here. So again, there are a number of approximations. You can just approximate it using a linear approximation. If you know the cracking strain that at which the stress becomes zero pretty much, so the ultimate failure one. You can use a bilinear approximation. So if you go to this reference over here by Hillerborg 1985, you can find the formulation for this bilinear curve, how to define it, how to define pretty much this point. There is as well the exponential one, which looks more closely to the actual nonlinear behavior of concrete in tension, the softening behavior. So again, this is a nonlinear one. So if you go to this reference as well, you can find the formula or the expression that you can use to generate this curve, again, that you can do in Excel very easily. But like if you look in the research, typically employing this one or that one, it doesn't really make much difference with respect to the results, as long as the fracture energy, which is called GF, which is pretty much the area under these curves. If the area under all these curves are similar, then it doesn't matter really if you employ one approximation or the other. All right. So this is for the tensile softening branch. And epsilon cracking, by the way, here when we are saying cracking here refers to the plastic strain. So when we are talking about on the tension side, we don't say inelastic or plastic strain, we typically say the cracking strain. In compression, we say inelastic strain or plastic strain. So this is just a matter of terminology to be aware of. All right, so how do we define this? So with respect to the elastic branch, well, this is pretty straightforward. In ABAQUS, you just need to provide the modulus of elasticity and the Poisson ratio. So that's straightforward. We are going to see an actual example with numbers later on. With respect to the definition of the plasticity part in compression and tension, well, in compression, you need to define the inelastic strain stress data under compression, which is the red portion here. So this is the red portion of the curve. And of course, if you are familiar with the definition of steel, for instance, you always start from the yielding point at strain equal to 0. So you define everything starting from this point. So this is the plastic strain equal to 0, and then, or the inelastic strain equal to 0, and then it goes higher inelastic strain. The same thing if you are looking in the tension, you need to provide the cracking. Again, we mentioned this in the terminology, so here it's called cracking strain. So you need to provide the cracking strain stress data under tension. Pretty much this green branch of the material curve, which, as we mentioned a second ago, can be approximated by any of those expressions, or if you have done a tensile split test or something on the concrete, maybe you already have this data explicitly. With respect to as part again of the definition of the plastic property, there are the plasticity flow parameters, and these parameters can be deduced from experimental data clearly, but typically we don't have this data in order to deduce this kind of parameters available. So in literature, there are many studies. I provide here some references if you want to read more about what each of these parameters represent. So you have the dilation angle, the eccentricity parameters, You have this ratio between the biaxial stress and the yield compressive stress or onset pretty much of compressive plastic deformations in compression, and you have this K factor and you have these viscosity parameters. So all these values that I'm showing here, these are the values that you will see in literature are typically used when you are defining the material model for concrete, and researchers don't tend to change those much. You can do a sensitivity analysis in order to get a sense of how these parameters will affect your model. But for most practical applications, if I'm looking at these 4 parameters over here, like the eccentricity, the sigma B0 over sigma C0, the K, the viscosity parameters, these 4 parameters don't affect much the behavior actually if you change those. Perhaps the most important one is the dilation angle, and this one ranges between 30 and 40. So this one perhaps that you could calibrate if you want to validate a model or something like that. Ideally, of course, you need to obtain this from some kind of experimental data or material testing, but if you don't have this, then just a matter of calibration in order to get those. But again, any number between 30 and 40 would be fine if you have no idea about like how to obtain this, or you are not validating something. But again, if you want to read more about this, these are a couple of references, and there are many more as well on the topic. Now we go to the damage part. So right now what we have defined earlier, this is the elastic part and the plasticity part, or the plastic part. These are the main parts of the material model. There is the optional one where you model the damage, and here damage means the unloading. When I unload, if I go to the plastic portion of my curve and at one point I unload. So when you unload, the stiffness that you unload with, typically you will have some damage because of the cracking and the plastic deformations happening in the concrete itself. So you are going to get lesser stiffness at each value of strain. So pretty much when we are trying to model this damage, we are trying to identify this parameter DC. So we want to say how much is this DC, which is pretty much the percentage loss of elastic stiffness as a function of the plastic strain. So of course, the more I go into the plastic range, the higher would be my damage parameter. And in theory, if I go to a very large plastic strain, then DC will tend to 1, and when DC is equal to 1, then the stiffness becomes 1 minus 1, 0, so it becomes 0, meaning there is no stiffness at all during unloading. So in ABAQUS, so again, these are some of the parameters that you have in the ABAQUS manual. These are the notation used in the ABAQUS manual. And pretty much what you need to provide here, you need to provide in ABAQUS, or the user need to provide in ABAQUS, you need to provide a data set. And this data set, pretty much you are telling ABAQUS at this inelastic strain, like if you are at any point, if you are at this inelastic strain, this would be the value of my damage parameter, and so on. So your damage parameter will go from 0. So you will start from this point where you have 0 inelastic strain, and the damage parameter is 0. And then the more you go with larger inelastic strains, the value of DC will keep increasing. We are going to see this in a second. So this is what you need to provide. Now, what will happen once you submit the job, once you run the analysis, ABAQUS will do the following. ABAQUS will internally compute the plastic strain. All right. So what is the plastic strain? It's this one. So you are going to compute the inelastic one and provide it in ABAQUS. And then internally, ABAQUS will actually compute this plastic strain. Now, this is the formula for computing the plastic strain. It's a very straightforward formula that you can deduce from this illustration I'm showing over here. But if ABAQUS computes the plastic strain, ABAQUS need to make sure, well, you need to make sure beforehand, if you are doing this in Excel, you need to make sure that these plastic strain values are always positive, that they don't go negative, that they are always positive, and that they are always increasing with increasing inelastic strain. If any of those two criteria are not met, then you are going to get an error, and ABAQUS will tell you that your parameters in the material model are not correct. We are getting negative values, or they are not monotonically increasing. So that's why you need to compute using this formula beforehand, like in Excel or something like that. You need to compute the plastic strain and make sure that your input data satisfies these criteria. The same thing applies with respect to the tension damage. The same thing, but now it's called, you just remove the subscript C and add a subscript T. That's it. And inelastic strain, now, as we mentioned, now it's called cracking strain, or CK, as a superscript here. So the same exact thing. Now, how are you going to get this damage parameter value? Well, ideally, this can be obtained from material testing. So here is an example. So ideally, the damage parameter is deduced from a material test with a ramped, unidirectional or asymmetric ramped loading unloading cycles as follows. So this is one example here from this reference over here. So you can see here in compression, so you load your concrete, you unload, you don't go to tension, and then you reload again, you unload, you reload, and so on. And then you can compute actually the damage parameter explicitly using this formula. So this is pretty much the ratio of the unloading stiffness at any strain divided by the elastic modulus of elasticity. So it's very, very straightforward. Now, of course, if you don't have this kind of data, you didn't conduct this kind of test, which most probably most of you do not have, then in the absence of such data, the damage parameter can actually be approximated as using this formula over here. So you just 1 minus sigma I, so whatever the stress that you are at, divided by the ultimate compressive strength. So this is an approximation. Again, in literature, you might find other formulas as well to deduce the damage parameter. The same thing applies if you are looking in tension. So again, you can do the same situation in tension, loading, unloading, and then you can evaluate explicitly the damage parameter. But if you don't have this kind of cyclic data, then you can just approximate dt using this formula over here. All right, so let's see example here. Just in the slides, I will show you pretty much how to do this. So I'm assuming here in my example that I have my stress strain data for both compression and tension. I will focus here on compression, but the same steps that I'm going to define here, you can redo in tension. So I have this data. This data can be obtained from, again, a cylinder test, compressive test, or you can just generate it from any of those expressions online. So this is the data in numerical form. I have the compressive strain, so this is the total strain, and this is the stress in compression again. So I start from 0 and I go to about 1%. So from this data, the first thing that you can do, we can directly deduce the modulus of elasticity, which is the slope over here. So this is the value that I get. I can deduce the yield point, sigma 0c, again, which is this point over here, and I can deduce the maximum compressive or the ultimate compressive strength, which is the crushing point over here. So this is the first thing. So now I can define directly the elastic branch, very straightforward. You need the Poisson ratio as well, which you can assume like 0.2 or 0.15 for concrete. Next step, we need to deduce the damage parameter. So we mentioned, in the lack of the experimental data, you can approximate, or like you can estimate the damage parameter using this formula. So you take all of these values here for sigma, the compression strength, stress, and you divide it by the ultimate compressive strength of the concrete, and then you get these values over here for the damage parameter. So you see here that the damage parameter is pretty much 0, 0 all the way, and you start getting some damage once you go beyond the yield point. So this is it for the damage parameter. The next step would be to compute the elastic and inelastic strains. So the elastic strain, this can be computed straightforward. Again, you take the stress, you divide it by the modulus of elasticity, and then you get the elastic strain. And then you compute the inelastic strain, and the inelastic strain in this case will be the total strain, so this one minus the elastic strain, and then you get this data over here. So in ABAQUS, what you are going to provide again is this inelastic strain and this damage parameter if you want to define the damage portion of the material model. But before you do that, you need to double check to make sure that the plastic strain will not be negative and that it will be monotonically increasing always. So before you input the data, before ABAQUS tell you there is an error, just do the check yourself. So compute, we deduce the plastic strain using the formula that ABAQUS will use. And then we need to check that all numbers are positive. So here I did that, and all the numbers look positive, so that's good. And I make sure that it's always increasing. Yes, it looks like it's always increasing monotonically, so that's fine. So now data is checked. So now I will go to ABAQUS, and then I will need to provide pretty much this point, which is the inelastic strain and the damage parameter. So if you plot it, this is how the evolution of the damage parameter look like with respect to the inelastic strain. That's it. The same thing, the same procedure exactly, step by step, should be followed if you are looking under for the providing the data for the stress strain under tension. So let's see how we input actually this in ABAQUS with the actual interface. So for the elastic property, again, you will go to the elastic under mechanical, you define an elastic property, and then you need to provide the Young's modulus, whatever it is, based on your data, and the Poisson ratio, again, whatever it is, based on your data or your concrete material. The second part, you need to go to the mechanical, and then you need to choose plasticity, and under plasticity, you need to choose concrete damage plasticity. The first thing that you need to provide, you have 3 tabs over here. You need to provide the plasticity part, and these are the flow rule again. So these are these 5 parameters. As we mentioned, again, those 4 parameters are more or less, they don't affect anything. The dilation angle, and it goes from 30 to 40. All right, so we just need to provide this data using the standard values used. Later on, again, as we mentioned, you can use or change this dilation angle in order to calibrate something against experimental data. The next thing is if you click on the other tab, you need to provide the compressive behavior, and here you will just need to insert the stress strain data of the inelastic branch. So starting from the yield point, all right, the end of inelastic branch. So you just need to copy this data from your Excel and just paste it over here. That's it. Similar to what you do with steel material definitions. Then if you click on the other tab, the tensile behavior, again, I'm going to define everything with respect to strain. Copy again the data starting from the ultimate tensile capacity or the cracking strength pretty much, and the cracking strain. So here again, notice that here it's called inelastic strain under compression, and in tension it's called cracking strain, but in both cases they refer to an inelastic behavior. So you just paste this data. You have another option here if you have this data in terms of stress displacement. So there is another option here from this drop down menu that you can define the tensile behavior based on displacement. So instead of providing strains, you provide actual displacement values in whatever the units that you are using. So that's it. This concludes the actual behavior of the material. Now, if I need to include the damage, then you will just need to go to the sub option, and from the sub options, you can select concrete damage in tension or in compression. or both. So if we go here, if I select concrete damage, compression damage, so in this case, as we just mentioned a second ago, we need to insert data for the inelastic strain and the damage parameter. So the inelastic strain and the damage parameter, I just paste the data like this. This tension recovery, this refers to the unloading. Again, when we are talking about damage, we're talking about unloading, reloading stiffness. So if I'm unloading from the tension, from the compression part under compression, if I'm unloading in compression and then I'm going now into tension, so should I maintain the same unloading stiffness or should it deteriorate? So by default, if you don't put anything here, the default is 0, and this is called omega t, this parameter, the tension recovery parameter. So by default is 0, and this means that the tensile stiffness is not recovered as the load changes from compression to tension once crushing microcracks have developed. So this is the default. You can just put 0 here, but even if it's empty, it means it's 0. That's it. Make sure that you're always use consistent data. So this column of data here for the inelastic strain, this has to be similar to the one, or it's recommended that it's the same vector of data like the one that you had here as well. All right, so if it changes, that's fine, but ideally, since you are getting all of this from an Excel sheet, most probably, then everything should be consistent. If you go to the tension damage behavior, again, you are going to do the same. So you need to provide the damage parameter in tension with respect to the cracking strain data again. Here, the compression recovery value, this is 1. You can put this 1 and 1. This is the default value. So this is omega c. So this means that the compressive stiffness is recovered upon crack closure as the load changes from tension to compression. So again, from this illustration from the ABAQUS manual, you can see what this means. Okay, so you don't maintain the unloading stiffness from from the tension side. No, you gain in strength. And this makes sense because, of course, when you are going into compression, you are closing gaps between the cracks and then you are picking up in stiffness. And this is the node that I just mentioned. Make sure that the data you are using pretty much the same data sets that you had defined earlier in the actual plasticity part. The final thing, that's it. This concludes actually the definition of the material with the damage. Now, if you are interested in visuals and you want to include failure, material failure, and by failure here I mean complete failure of the concrete, so not just damage but complete failure of the concrete. So if you want to simulate that and you want to also to visualize some element deletion, maybe for visuals, you want to see that in your animation. So in order to model this, to define concrete material failure, you can't do this from the interface. It's not implemented yet in ABAQUS interface. So instead you need to add it using the keyword option to the input file. So if you right click on your model in the tree section of your model in your interface, and if you select, not edit attributes, you should select edit keywords. If you select edit keywords, this is a mistake here in the screenshot. So you just need to select edit keywords, and then if this will open the input file for your model. If you scroll down, and then you can insert this command over here using the same syntax that I'm showing over here. So you just need to have an asterisk, then concrete failure, and then in comma type equal strain, and then you need pretty much to provide the failure strain in cracking and the failure strain in compression, the inelastic one. Basically, this is the compression and this is the tension, and the corresponding damage values at which failure would be assumed. In this example that I'm showing over here, actually I'm using the values from the last data points from my tension damage and from my compression damage like this. And after you finish, you just need to click OK, and that's it. So this means that you have defined complete failure of your concrete. And then the next thing, if you want to activate element deletion, when you define the mesh element, so this is just a matter of a visual representation, so this is not an actual thing in the material model. So from the mesh module, from the mesh module, when you are selecting your mesh element, you just need to scroll down here in the options and you select yes for element deletion from this dialog. And you can change here the maximum degradation. By default it's 1, but if you want, you can specify a different value if you want. Again, this is up to you, or you can just use the default. So this is how you visualize the element deletion. All right, that's it. And also, yeah, you need to also to check, in order for this to work, you need to in most cases you need to modify the field output history. So make sure in the field output history that you include the damage parameters. So this is under failure. There are these damage parameters: damage compression, damage tension, and damage in shear. Make sure that you select those to include. As well, there is a field variable called status. If you go all the way down, again, select this one as well. That's it. This is again for the visualization of element deletion. That's it. This concludes this quick video tutorial on what is the concrete damage plasticity material model is defined in ABAQUS. In the next video, we are going to see how we can apply this and to do an actual compression cylinder test, which is pretty much the most basic problem that you can do to play with these parameters and investigate how they will affect the behavior of concrete. So this is what we are going to do in next video. We are going to model a concrete cylinder with these dimensions, with a fixed end and some displacement control loading from the top, and we'll see how damage will happen. So we'll see you in the next video.